This is part 7 in the series of videos in which I am repairing an IBM 5120 computer. I've got as far as stripping down the power supply module, and I'm in the process of replacing the mains cable. The original was cut off short, so I need to replace this. But as with everything else on this machine, it requires quite a large degree of dismantling to actually get to the connections on the mains cable. So they're connected for some reason to the wrong end of the filter, and so I need to feed the cable through, fit some ring terminals, get it reconnected, and then I can test this particular part of the module. This really just comprises of the inlet cable, the breaker, and this is just a 5 amp breaker. It's got a trip current of 6.25 amps, the main switch, and then that's fed through to the main power transformer. There are also AC outlets that go through to the floppy drives as well. An additional mains is distributed around the system for things like the monitor and other various bits and pieces on the machine. So I'll get this mains cable replaced, and then once I've checked everything else on this part of the sub-assembly, we'll power it up using the Variac and see if it comes back to life. So I've prepared the ends of the new mains cable so it matches the lengths of the original. I can now feed this through into the box. I'll route it the same way it was originally. Okay, I have the new cable connected. Made sure the ground connection is nice and secure. Check that they are wired the same as the original, and what I can do now is fit the strain relief onto the cable. Okay, that's the strain relief in place. The cable's secure. It's not going to pull out. There's plenty of slack in the earth lead. And what I can do now is refit the remaining parts. So we've got the breaker box. So that's the breaker fitted. And now the main switch. So the main switch is adjustable because it needs to be adjusted to line up with the opening in the front of the machine. So I'll get that reattached, but I'll leave the screws loose for now. I'll need to adjust that once I've got this reinstalled. So I've got that in place, but it will move, so I can get it lined up with the case once this is refitted. I'll now tidy up these cables, make sure they're sitting so they won't get crimped or snagged, and then we can actually power it up. I've tested all the components on here that I can, and they all seem fine. So the next step will be to hook it up to the Variac and try powering it up, and that will be the first part of this machine to actually see some power. I've got the power supply hooked up to the Variac. I've checked again to make sure that nothing's shorted. I've measured across the mains input, and the input does look fine. It's what I'd expect with the switches and the breaker in the on position. What I can do now is turn the breaker on, turn the mains power switch on, and I can now turn on the Variac. And this is wired directly across the mains output of the filter. So what we should see here is the mains voltage that we're feeding into the power supply. So I'll start to increase this. I'm keeping an eye on the current on the Variac to make sure that we don't have any excessive current, and that does appear to be going a bit higher than I would really like, so I'm going to turn this back down and investigate a bit further as to where that power is actually going to. As we saw, as I raised the input voltage on the mains supply, the input current started to rise very rapidly, and by the time I'd got to 80 or 90 volts it was already up near half an amp. That tended to imply that by the time we got to 240 volts we'd be up near 2 amps, so something didn't seem quite right. There's no load on this supply, so it should be drawing probably less than 100 milliamps. And the only losses really should be in the transformer itself. So I had a dig around, and luckily in the service manual I do have, there is this wiring diagram. There's no wiring diagram for the electronics, but this is the interconnect diagram for this module. And looking through this, I got down to the bottom here and we have this arrangement, and then it kind of started to make sense. They are generating a floating 240 volt supply for the CRT. I'm not sure if they're doing this because they don't have a 120 volts CRT, or if there's some other reason why they need a floating supply for this, maybe for safety or something like that. But either way, they've gone about it in a bit of an odd way, and that they're using a capacitor to generate, or to effectively generate another phase from the main supply. And so they have a center tapped winding on the transformer. The center tap goes to ground, and then the capacitor is used in order to generate the second phase of the supply, and that then generates 240 volts AC that goes to the CRT. But because this arrangement requires that the capacitor be resonant at the normal balanced load, then what can happen is at partial load or partial voltage, then this won't really work very well and we'll get some fairly odd behaviour, and I think that's what was happening. So unfortunately the only way to prove this is to turn the voltage up higher. It is fused of course, and there is a trip, and I am using the auto transformer, but even so it's still a little bit of a risk. I've checked the capacitor again and it seems fine. I've done a full leakage test. There's nothing else on here. When I disconnect this, it stops doing it, so that is, it stops peaking the current, so it's got something to do with this certainly. That's actually this arrangement that I showed earlier. It's a very peculiar arrangement, but I think it's just so that they can have the fuse close to the CRT. Okay, so as I said, the only way to proceed really is to turn the supply voltage up further, and I think what should happen is the current should peak and then go back down quite significantly, and we can keep an eye on the voltage coming out of the supply at the same time, so the test meter is connected to this point here. Okay, so I'll power up the auto transformer and see what happens. So you can see the current's rising very rapidly. We're coming up to around 0.5 amp, and it is making quite a lot of noise. It's now starting to make very strange noises. I'll keep going up. I'm hoping that it's going to start dropping again, which it has. Okay, so at our 240 volt nominal input voltage, we are seeing about 100 milliamps, so that's looking quite promising now. We're getting the correct output voltage, of course. Nothing's smoking. The transformer is buzzing a bit, but it's not too bad. Old transformers do tend to do that, and of course this won't be audible over the noise of the fans in the machine. So what I'll do, I'll leave it running for a while and see if anything fails. I'll keep an eye on it with a thermal camera, and then once it's had a run for a while, I'll retest everything, check the capacitor again for leakage, and if all's well, then I'll put the end cover on, and we can start testing the output on the transformer secondaries. Okay, it's had about an hour and nothing's really getting warm. It seems to have settled down quite well. It's carried on making the same buzzing noise, but as I said, that's not surprising. But nothing's getting hot. What I'll do now is I'll turn off the power, I'll leave it for a while, and then I'll come back and I'll retest the capacitor and the filter and make sure that they're still not showing any significant leakage. Well, it's all checked out fine, nothing's leaking, the capacitor still seems fine, the filter's fine, nothing's getting hot. It's been on for over an hour and the transformer is barely warm. It's not really heated up at all. Still buzzing, but as I say, it's just an old transformer, and I think that's just the noise it typically makes. If anyone that's interested, there is a a test sticker down here that's dated the 11th of the 8th 1980, so that may be the original PAT test that was done on this. So it gives some idea as to its age. We know it's at least 1980, if not older. So next step is referring to the diagram I showed a few minutes ago. Then what we can do is measure the voltages coming out of this connector, which is this one. This is the one that connects to the capacitor board. So I'm assuming that board is responsible for rectifying these voltages and smoothing them. So what we're looking for are 3 center tapped windings, and you won't be able to see the diagram, but I'm going to measure between each of the pins and see if we're getting the voltages that we expect. So I'll power it back up. Then looking at the connector, I believe this is pin 1. So what we should have to start with is center tapped plus or minus 24 volts, with the center tap being pin 6. So I'll put one probe into pin 6, and then pins 1 and 2 should be the at each end of the winding. So the first one should be, that's fine, and then the other one should be pin 2. Okay, and then we should get double that if we measure between pins 1 and 2, which we do. And then the next winding is again center tapped plus or minus 5 volts, with pin 5 being the center tap, which is that one, and then pins 7 and 8 being each end of the winding. So it's 5 volts on that one, 5 volts on that one, and then we should get around 10 volts between the 2 ends of the winding, which we do. And then the last one is plus or minus 5 volts again, but this is for the minus 5 volt supply, but obviously this is the AC side, so it will read the same. And the center tap is pin 4, and the first end of that winding is pin 3, 5 volts, which is correct. And then the other end of that winding is pin 9, which should be this one, and then we should get around 10 volts between pins 3 and 9, which we are doing. So that's all reading correct. So it looks like the transformer is fine. Obviously this is not loaded, so we'll have to give it a full load test. But what I'm going to do now is turn my attention to the rectifier board. So that's this board. So we'll get the supply chassis out of the way and start looking at that board. So we can turn our attention to the rectifier and filter board. I believe this is just here in order to rectify and smooth the 3 supplies from each of the 3 transformer windings. We seem to have 3 sets of rectified diodes. It's odd that there's a mismatched pair here, so it looks like one of these may have been changed at some point. And then it looks like we've got some bleeder resistors to discharge them. These are wired directly across each one, so I think they're just there to discharge the capacitors when the power's turned off. And then of course we've got a fuse for each of the 3 supplies. So I think this just takes the 3 raw center tapped AC supplies, rectifies them, smooths them. These 2 connectors go to the floppy disk drives, so it looks like that's all this does. It seems to just be the supply for the floppy drives. It doesn't seem to go anywhere else, and it looks like the other board in the supply is the one that generates most of the series supplies for the rest of the machine. So what we'll do with this first is take the capacitors out. I'll test them individually, and then we can also test the other components on the board. So I'll just get these removed. Okay, that's the 3 capacitors out of the way. What I will do now is just test these rectifiers and the resistors to make sure they're fine. So we'll get the test meter in, put it into diode test mode, and then we'll see if these devices actually work. So those two are fine. And those four are fine. We'll just test the resistors while we're here. So the first one is 26 ohms. Close enough. And then we have 51 ohms. And finally 750. Which is fine. So looks like this board's fine. I will give it a clean. It's not too bad, but I'll clean it anyway. Next thing to do is test the capacitors. Okay, the way I'm going to test these capacitors is I'm going to connect them to the bench power supply close to their rated voltage, and I'm going to leave them running for 24 hours and keep an eye on the leakage current to make sure it doesn't start rising. I have to be very careful with this supply because, as I mentioned in the previous video, the modules in the IBM machine are extremely difficult to replace, and I don't want to damage them by plugging in a supply that's going to cause problems. So I want to be absolutely certain that the supply is working 100% before I try applying power to the machine with it. So I'm going to be careful with things like this, and by the time we finish going through the supply, we need to make sure it's working 100% and not going to destroy anything. So we'll start with the first capacitor. We'll use channel 1 on the bench supply. So we'll get it connected up. Make sure I've got it the right way around. And I will set 30 volts, and we'll set it at 0.1 amps. Current's not really important, it's just to limit the current if there's a problem with the capacitor. We'll turn it on. The voltage should go up to around 30 volts, and then the current should drop to fairly close to zero. There will be some leakage, a few milliamps maybe, but any more than that will indicate that there's a problem. And more importantly, it shouldn't go up throughout the test. Okay, onto the next capacitor. So we use the next channel for that. And this is a 10 volt capacitor, so we'll test it at the full rated voltage. So we'll set channel 2 to 10 volts, again limited to 0.1 amp. Turn it on, and then that should stabilize at 10 volts, and the current should again drop very close to zero, which it does. And then onto the third channel, connect up the capacitor. I'm going to set this channel to 5.3 volts, that's a maximum for this channel, and it's fine. This is on the 5 volt supply, so that should be enough. I'll set this to 200 milliamps because it is a very large value capacitor, and I wanted to charge up in a reasonable speed. Okay, so what we've got at the moment is all three capacitors are connected to quite a good percentage of their maximum voltage rating. The first one has settled down, it's down to around 1 milliamp. It's flicking between 0 and 1 milliamps, a very good low leakage. The second one has now settled down to 3 milliamps, it probably will drop a bit further. And then the last one is currently down at 5 milliamps, and again that may well go down further. And the idea here is we'll leave it running overnight, and if the leakage current rises significantly or there's a catastrophic failure, then obviously this is quite a good way of testing them. If they survive for 24 hours, then we can be fairly confident they'll survive in the machine. Now, this is not a particularly in-depth test because there's no ripple current on the capacitors, and often it's ripple current that causes them to heat up and possibly fail. but there is a limit as to how much testing we can do with them not in the machine. What we will do is, once we've established these are working like this, we'll connect them to the electronic loads with them fitted back to the rectifier board, and then we'll test all three supplies under load and make sure that's working fine, because that will put them under a ripple current test. And then we'll move on to the main board on the supply and do pretty much exactly the same thing. It is a switching supply, so it'll be more difficult to test, but once we've established that it's working, again we'll test it under full load for 24 hours and make sure it's working fine. And on the assumption that everything's behaving itself, we'll put everything back together and then test the entire supply under load, and it will be ready then to go back into the machine. The capacitors survived the soak test. They had 24 hours connected to the lab supply. The leakage current didn't increase, it stayed nice and steady, very low, around 1 to 2 milliamps, and they didn't get warm, and the capacities all seem fine. So I've refitted them to the board, and I've refitted the assembly and the mounting bracket back into the power supply chassis. As you can see, I now have the board hooked up to 3 electronic loads. I mentioned previously I was going to buy some more of these loads for various projects, and this is one of those projects that I needed them for. As ever, apologies for the flickering on the loads. I can't prevent that, it's just an artifact of my camera shutter speed. Hopefully it won't be too annoying. And what I've done is I've set them up so that they apply a load to this supply that matches the currents that will be drawn when the supply is in the actual machine. This supply, or these supplies, only feed the floppy drives. So what I've done is look at the specification for the floppy drives in terms of the current drawn on each rail. I've doubled it because there are 2 of them, and that's what I have the electronic load set to. This has now been running for about 3 hours and nothing's getting hot. It's all running exactly the way it should do. I've checked the ripple voltage, and that's well within specs, very low as you might expect with such large value capacitors. And this is of course a proper ripple current test because we are running it at full load. As you can see, I don't know if you can actually read the mains values on the auto transformer. So we've got it set to 220 volts. It's at 0.17 amps, which is fine. It's well within what you'd expect in terms of the efficiency, considering the power that we are pulling out of this. And as I say, it's been running for a while now. I'll leave it another hour or so, and if nothing gets hot, then we'll move on to the main PCB in the supply. So it's time for the big moment. I've got the main power supply control board hooked up. I have spent quite a lot of time going through this and checking as many parts as I could. I removed the main smoothing cap and did a full leakage test on that. I have removed a few of these and tested them, and they test okay. They're not brilliant. The leakage is slightly high and the capacities are a bit lower than expected, but they do seem fairly reasonable. I think the best course of action with these is, if we get the machine running, then just replace all of these before it is put back into any sort of service. I've gone through all the rest of the parts, and I can't find any shorts. I've disconnected all the power devices and checked them in as many ways as I can. So if it's a diode, for example, I've disconnected it and done a full diode and current test on it. I've checked all the other caps for shorts. I've checked all the power resistors to make sure they're within spec. Everything seems fine. I've given the board a really good clean as ever, and it all seems okay. As I say, there are some of the SLT modules on this board which I can't test directly. I have looked them up. I do have the specs for these, but they are quite hard to test because of the physical layout of them. But if we need to, we can look at these, and if worst case, we can always make up some replacement modules. Okay, so I've tested it as far as I can. Unfortunately, with a switch mode supply like this, the only real way to test it is to switch it on, and that's what I'm going to do now. I have the meter hooked up to the what should be a 5-volt rail, reference to ground, and we should see somewhere around 6.5 volts to 7 volts. It is completely unloaded, of course. according to the specification, then we should be seeing probably something in the region of about 6.5 to 7 volts, and it specifies it with what they call the Y1 cable disconnected. Anyone playing along at home, that's this cable. This is the one that plugs into the motherboard in the electronics box. But with everything unplugged, the voltage will be slightly higher. And so what I'll do now is power it up. If the voltage goes too high, the over voltage current or current limiting should come in. If it's under volts, then again the supply will shut down. It's got undervolt and overvolt and overcurrent protection in theory. So if we see anything on the output at all, it's a fairly good sign that the supply is at least switching. If it goes very high and tries to shut itself down, then it could be there's a faulty power device. But as I say, I've tested them as far as I can, and the next step is to switch it on. As far as I can tell, 2 of these devices are configured as a switch on delay, and it seems to stagger 2 of the supply voltages. I think it wants to bring up the logic rail before it brings up one of the higher voltage power rails. So it might take a few seconds when we first switch it on before it does anything. This does make kind of a weird noise anyway, so it's kind of hard to tell if it's under any stress, but I'll switch it on now, see what happens. We'll keep an eye on the current on the auto transformer. If that goes too high, I'll switch it back off, and fingers crossed, let's see what we get. Okay, well, we're getting just over 7 volts on the output of the 5 volt rail, which seems a bit high. Maybe half a volt higher than I was expecting, but as I say, this is completely unloaded, so that's perhaps not all that surprising. I'm going to turn it off now and get a flying lead on the test meter so I can test the other rails and see if they're all around what they should be. Okay, now I have a test probe on the meter. The reason I had it clipped on when we did the first test is I wanted an immediate display. I didn't want to have to start probing around if there was something wrong. So if we got, for example, 12 volts on there, I wanted to be able to turn it off straight away. But now we know it's behaving to a certain extent, I can hopefully fairly safely start probing around and seeing what the various voltages are. I need to be fairly careful. There is a very high voltage over on this end of the board. It is rectified mains, so it is around 400 volts. I need to be fairly wary of that. So what I'll do is switch it back on. We'll look at the various voltage lines. They are indicated on the board as to what they should be, and so I'll power it up. If you recall, with just this board fitted, we were getting about 170 milliamps. We're now getting 210 milliamps, so it's only gone up by 40 milliamps to drive this switching supply, which is quite promising. It means that, at least in theory, nothing's absorbing much power. Okay, so I'll start probing. We'll go back and look at the 5 volt again. That was 7.2, still is. And we'll go on to the next one. It's supposed to be 9.5. 12. Minus 12. And finally, minus 5. So they're looking fine. The only one that's out by any large degree is the plus 5 volt rail, but that's a very high current supply rail, so it's perhaps not surprising that it's showing high. There is an adjuster pot down on the board, so I want to try and investigate what that's for, whether or not we can turn this down a little bit. And also now I'm going to apply a small load to the 5 volt rail and see if that comes down. It might just be a case that it's floating quite high because there's such a light load on it. I'll also hook up the scope and we'll just make sure it is switching and that it's not a case of the driver transistor just turning full on and us seeing the raw supply coming through to the output. Okay, I have the scope hooked up. I've attached a 200 ohm dummy load to the 5 volt rail, and I have the multimeter attached directly to the 5 volt rail. So the word of caution here, if you do attach a scope to a supply like this, make sure that you're using something that it is safe to earth reference. Dave Jones over on EEV blog posted a video quite a while back about the dangers of how not to blow up your scope, and is something you do need to bear in mind, that you don't want to put in place a short to ground from anything that's mains referenced. Okay, but this is a floating output on this supply, so it is safe for me to clip the ground lead from the scope to it. I have the scope connected to the 5V rail as well, and what we're looking for is some evidence that there is switching going on, and also that the supply is relatively stable. What we don't want to see is a lot of huge spikes on there, or anything that looks peculiar. We should be seeing a fairly flat trace. Okay, I'll turn it back on. So the scope's looking good, and we can see we're down now slightly under 7 volts, which is more along the lines of what I was expecting. Very light load is about 30 milliamps being drawn out of the 5V rail, and it should be able to supply between 5 and 10 amps. So that's quite promising. What I'll do off camera is give it a full load test. I'll connect it to an electronic load, put all the lines through their paces, make sure that they're all able to supply the power they're supposed to. I won't do it on camera, it gets a bit tedious, but if I do find anything, I'll come back on camera. If not, then in the next video I'll get this reassembled, I'll get the cover repainted, fully assembled, and then we'll do a final test before refitting it to the chassis.